optimization today. And let me get my screen here. Optimization is just what we've been doing, which is finding maxes and mins, and we're going to use some real world application to optimize area, optimize revenue, those kind of problems. So take out these notes and we'll get started. Find the dimensions of a rectangle with a perimeter of 200 feet and an area as large as possible. Okay, so there's always going to be two equations we're going to talk about. And so when you are dealing with rectangles, you should remember from geometry class that the two equations you work with are area, which is length times width, and then perimeter. Now, we want to maximize this area. When it says find an area as large as possible, so that's a max. This is what's known as our objective function. So the other piece of information we know about is the perimeter. So remember, perimeter means walking around here, so 2L plus 2W. But if we know the perimeter is 200, we're going to say 200 equals 2L plus 2W. This equation is called the constraint. So you're going to take the constraint equation and you're going to solve it for one of these letters, for L or for W. It doesn't matter. And I'll just solve it for W, I guess. So I would have 200 minus 2L equals 2W, and then divide everything by 2. 100 equals 100 minus L equals W. Once you solve the constraint equation, you're going to then plug it into the objective function, replace it into the objective. So you're going to have this objective function, which you started off with, and you're going to replace that W with this expression 100 minus L. So L times 100 minus L. And you'll get 100L minus L squared. And then just like anything involving max and mins, we're going to have to take a derivative. So we're going to take a derivative of A. We're not doing it with respect to time. We're just taking it with respect to whatever variable we have, in this term's length. So that would be 100, and the derivative of L squared is 2L. You're going to set it equal to 0, and you're going to solve. So we get L to be 50. Now, verify that this is a maximum area. To verify, remember, you take a second derivative. So the second derivative of this would be negative, well, it'd be -2, but negative means that you are concaving down, which means you must be a max at 50. So if L is 50, plug it back up to here to find W. W would also be 50. So we would have to have a 50 by 50 rectangle to create the largest area. That was a very easy one. Let's do a little bit harder of a problem. So a farmer has 600 feet of fencing, so there's perimeter again, and wants to create a rectangular field along a river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So again, you have this river. You're going to draw this rectangle. You don't need fence on that side. So I would have length times width, or length times width would still be the area. That would still be my objective function. The perimeter would change. Now it would be 600 equals 1L plus 2W. Now solve this for a constraint. I mean, you could solve for W again. I'm just going to solve for L because it's easier. So you'd have 600 minus 2W equals L. And then remember what I did before. I took this expression and I plugged it into the objective function. Everywhere I saw an L there. So area equals length times width. Instead of L, area equals 600 minus 2W times W. So that would be 600W minus 2W squared. Now we're going to take a derivative of that. 600 minus 4W. We're going to set it equal to 0. And we get W to be 150. And again, verifying that this is a max, you take a second derivative. Second derivative of this would be 0. The second derivative of that would be -4, which means it's negative, which means it's concave down the entire time with a max. So if the width is 150, plug it back up here to find the length. 600 minus 2 times 150. You would have a length of 300 and a width of 150. That would give you the maximum area. Let's try another one. A farmer wishes to create a rectangular field along a river with an area now. Oh, now we know more about the area. So the perimeter is what we know the least about. So the perimeter is going to become our objective function. So we have that same picture again. So this time our perimeter is 2W plus L. That's our objective. We know more about the area. And so area, again, is length times width. So I'll just say 10,000 equals length times width. This is our constraint now. We're going to solve this for a variable. Again, doesn't matter. I'm going to solve for L. So 10,000 divided by W is L. I'm going to plug that into my objective. So P equals 2W plus 10,000 over W. But watch how I rewrite this. I'm going to rewrite this as 10,000 W to the -1. Because remember, you want to take a derivative of that. So the derivative of P with respect to width would be 2 minus 10,000 W to the -2. And we're going to set that equal to 0. And I'm going to put that W squared back down. I'm going to put it over 1 and do some algebra. So 2W squared equals 10,000. W squared equals 5,000. And take the square root of W, which is about 70.7. Now let's verify that this is again, what are we finding? What are the dimensions of the field requiring the least amount? So I'm finding a min. So let's take a second derivative. This would be 0. This would be positive 20,000 W to the -3. And if you put the 70.7 into the second derivative, oops, you would still get out a positive number, which means that you are concaving up, which means you must have a min. So my width is 70.7, and then plug it right back there to find the length, and you would get a length of 141.4. Those would be the dimensions. All right. Let's kind of switch from doing these rectangles to now a three-dimensional picture. What is the largest possible volume of a box with a square base and an open top that can be produced using 900 centimeters squared of material? So I know that I have a square base, and that is important down here. If you remember, the formula for a volume of a box is usually length times width times height. And that's usually our volume. But if these are the same, I'm just going to call it L and L and then call that height. So my volume would be L squared H. So that's my objective function. What is the largest possible volume? Now we need another formula. Well, you remember, let me draw this off to the side. There is a formula for what's called surface area. So if I have a box and I know that this, I have, if you remember, 6 sides to a box, the bottom would be L squared as an area. The sides would all be, this side would be L by H, so 1LH. The back would also be another LH. This side would be LH. The front would also be LH, but the top, remember they told you, was open. So I have an L squared on the bottom, and then I have 4 sides going around, so 4 LHs, and then the top is open. So this would be my surface area formula. So that's the second formula I'm going to use. So I'm going to write surface area, which they told us actually up here was 900 centimeters squared of material. So 900 equals this formula, L squared plus 4LH. And I'm going to solve for constraint. Well, the best constraint to solve for is H, since it's a variable by itself. So it'd be 900 minus L squared, and then divide by 4L equals H. Remember what to do? You're going to take this, you're going to plug it into the objective function and replace it there. So we would have volume equals L squared times 900 minus L squared over 4L. We got to clean this up. So L squared times 900 would be 900 L squared divided by 4L. And then this one would be minus L to the 4th divided by 4L. Now watch how I rewrite this, because remember, we have to take a derivative. 900 divided by 4 is 225. L squared divided by L is just an L. If you're dividing by 4, that's the same as saying 1/4. L to the 4 over L is L to the 3rd. So that is the volume that we're going to take a derivative right here. The derivative of the volume with respect to L would be 225. 3 times 1/4 is 3/4 L squared. Set it equal to 0, and let's start doing some algebra. We're going to divide by 3/4, which is multiplying that by 4 over 3, which is 300. So L is roughly 17.3. And again, you can take a second derivative of the volume, and you would get a 6/4 L. Plug that 17.3 inside of it and see if it's still negative. It is. That means you must be concaving down, which means you must have a max. So if L is 17.3, how do you find height? You just plug L right there and right there into this solved constraint. And your height would be roughly 8.67. And then if we were finding the volume, we would do length squared times 8.67, and we get a volume of approximately 26.01 inches, centimeters. Whoops. So that's how you would do a problem with an open box. And then one more. I'll do part 2 in the next video. Find the dimensions that will minimize the cost of metal to make a cylindrical can that can be able to store 250 centimeters cubed of fluid. Again, if you don't remember your equations for cylinder, you have a height and a radius. So volume equals pi r squared h is the volume for any cylinder. And we were actually told we know a little bit of the volume. So that's not our objective. That's actually one of our constraints we'll use to solve for a constraint. So we need to find the cost of metal to make the outside of it, to make the wrapping around. That's surface area. So surface area for any cylinder is 2 pi r squared, that's the top and the bottom of the circle, plus 2 pi rh. So this is our objective function. This one, we're going to solve for h. H is equal to 250 divided by pi r squared. Remember to replace this into the objective function for h. So I'm going to rewrite it to be SA equals 2 pi r squared plus 2 pi r, and then h I'm going to replace with that. And we need to clean this up, because remember, we're going to take a derivative of it. So the pi's will cancel. And I will have 500 over r. And then I will rewrite that as 2 pi r squared plus 500 r to the negative 1. Because you got to take a derivative of it. So let's take a derivative. Derivative of the surface area would be 4 pi r minus 500 r to the negative 2. Set it equal to 0 and do some algebra here. Let me put this over r squared. Put that over 1. You can crisscross multiply. You get 4 pi r cubed equals 500. You get r cubed equals divide by 4 pi, so that's 125 pi. And then take the cube root, so you have r to be approximately 3.41. And again, to verify that you have a max or a min, we're doing a min here, you would take a second derivative. This would be 4 pi. This would become 1,000, positive 1,000 r to the negative 3. And if you plug 3.4 in for r, you'll still have a positive number, which means you're concave up, which means you have a min. So my r is 3.414. My h, I would plug right back there, and I would get roughly 6.828. And that's part 1 of optimization. I'll do part 2 in the next video.